In a quiet data center, thousands of machines hum day and night. Most people think artificial intelligence is just software, but the truth is far heavier. Training a large AI model can require more electricity than hundreds of homes use in a year. Researchers estimate that modern AI systems rely on enormous computing clusters running continuously for weeks or months. The secret cost of training AI begins long before anyone types a prompt. In 2012, the famous AlexNet neural network shocked the world by winning the ImageNet competition. It used just 2 GPUs and trained for about 5 days. That sounded intense at the time. But today's AI models are millions of times larger. The journey from 2 GPUs to tens of thousands of chips shows how quickly the hidden costs of artificial intelligence began to grow behind the scenes. By 2020, the scale of AI exploded. Training advanced language models required hundreds of powerful GPUs working together. One study estimated that a single large model training run could emit over 284 tons of carbon dioxide. That is roughly equal to the lifetime emissions of 5 average cars. The promise of smarter machines came with a growing environmental price few people notice. Electricity is the first invisible cost. Training a cutting-edge model can consume millions of kilowatt-hours. Some estimates suggest a large AI training process may use as much electricity as a small town for several days. Data centers must stay powered 24 hours a day. Even a brief outage could erase weeks of expensive training progress. Cooling is another hidden expense. AI chips generate enormous heat when processing billions of calculations each second. Data centers rely on complex cooling systems that circulate chilled air or liquid to prevent overheating. In many facilities, cooling systems can consume nearly 40% of total energy usage, meaning almost half the power supports temperature control rather than computation. Water usage is rarely discussed. Many large data centers use water-based cooling towers. A single large facility can consume millions of gallons of water each year. Studies have estimated that training a large AI model may indirectly use hundreds of thousands of liters of water, especially in regions where cooling systems rely on evaporation to remove heat. The hardware itself is expensive. Modern AI training depends on specialized chips such as GPUs and AI accelerators. A single advanced GPU can cost between $10,000 and $40,000. Training a frontier AI system may require thousands of these chips working together, pushing the hardware budget into the hundreds of millions of dollars. Building the computing cluster is only the beginning. Engineers must connect thousands of processors through ultra-fast networking systems. These connections allow chips to exchange data at incredible speeds. High-performance networking equipment can cost tens of millions of dollars alone, because even a small delay between processors slows the entire training process. Then there is the cost of data. AI models learn by analyzing enormous datasets collected from the internet, books, articles, and images. Some datasets contain hundreds of billions of words. Collecting, cleaning, and organizing this information requires large teams of engineers and data specialists who work for months before training even begins. Human labor is another overlooked factor. Many datasets must be labeled by people so machines can understand patterns. Around the world, thousands of contractors review images, text, and videos to mark objects or classify information. Some studies estimate that hundreds of thousands of human hours go into preparing data for large AI systems. Researchers also spend significant time designing the model itself. Before training starts, teams experiment with architectures, parameters, and optimization strategies. These experiments require smaller training runs that still consume large amounts of computing power. By the time the final model begins training, dozens of earlier versions may already have been tested and discarded. The first full training run often fails. Large AI systems are complex and unpredictable. Engineers sometimes discover software bugs, unstable algorithms, or unexpected behaviors. When that happens, weeks of computation can be lost. Restarting the training process means repeating millions of dollars worth of energy and hardware usage. Cloud computing platforms have turned AI training into a massive industry. Companies rent clusters of GPUs to researchers and startups. Hourly costs for powerful AI hardware can exceed several dollars per chip. When thousands of chips run simultaneously, the hourly cost can climb to tens of thousands of dollars. Some estimates suggest that training the largest modern language models may cost between $50 million and $100 million. This includes hardware, electricity, engineering labor, and data preparation. Only the largest technology companies or well-funded research labs can afford experiments at this scale. Electricity pricing also matters. Many data centers are built in regions with cheap power, such as areas with hydroelectric dams or large renewable energy projects. Lower energy costs can save companies millions of dollars during long training runs that operate continuously for weeks. Carbon emissions remain a growing concern. Data centers worldwide already consume about 1 to 2% of global electricity. As artificial intelligence expands, researchers warn that AI training could become a major contributor to global energy demand unless efficiency improves dramatically. Efficiency improvements are happening. New AI chips are designed to perform more calculations per watt of electricity. Companies also develop smarter algorithms that reduce the amount of computation needed. Even small efficiency gains can save millions of dollars when multiplied across large clusters running for months. Despite improvements, the demand for computing power keeps rising. Each new generation of AI models tends to grow larger and more complex. Some systems now contain hundreds of billions or even trillions of parameters, meaning the number of internal connections the model must learn during training. Training such enormous systems requires careful coordination between thousands of processors. Engineers divide the model into sections so different chips can process parts of the network simultaneously. This technique, called distributed training, allows massive models to learn faster but also increases system complexity. Time is another cost. A major AI training project may run for several weeks or months without stopping. During that time, thousands of machines operate at full capacity. If a failure occurs near the end of training, the financial loss can be enormous. Some researchers estimate that large AI projects require billions of trillions of mathematical operations during training. These calculations happen at astonishing speed, with modern chips performing tens of trillions of operations every second. Behind every AI breakthrough is an enormous infrastructure. Giant data centers filled with servers, cooling systems, networking cables, and backup generators support the process. These buildings often resemble industrial factories more than traditional computer rooms. Companies also invest heavily in backup systems. Power outages, hardware failures, or network interruptions could halt training. To prevent this, facilities install redundant power lines, battery systems, and emergency generators capable of running entire data centers. Security adds another layer of cost. Valuable AI models represent billions of dollars of intellectual property. Data centers must protect hardware, data, and train models from cyber attacks and physical threats. Security teams monitor networks continuously to prevent unauthorized access. Once training finishes, the expenses do not stop. Engineers must test the model extensively to ensure it performs reliably. Evaluation requires running the system on thousands of benchmarks and real-world scenarios to measure accuracy, bias, and safety. After testing comes deployment. Running an AI model for users requires additional servers that respond to millions of requests each day. These inference systems often use separate hardware clusters optimized for fast responses rather than training speed. Maintenance continues throughout the model's life. Engineers monitor performance, update software, and retrain models with new data. Each retraining cycle repeats many of the same costs involved in the original training process. Competition between companies drives costs even higher. Technology giants invest billions of dollars annually in AI infrastructure. Building larger models can provide competitive advantages in search engines, recommendation systems, and digital assistants. Governments are also entering the race. National AI strategies in countries around the world include plans for supercomputers dedicated to machine learning research. These facilities cost hundreds of millions of dollars but promise strategic technological advantages. The semiconductor industry benefits from this demand. Companies producing advanced chips now compete to supply AI data centers. Manufacturing these processors requires extremely complex factories that can cost over $10 billion to build. There is also a growing debate about sustainability. Researchers are exploring ways to train AI models using renewable energy sources such as solar and wind power. Some data centers are being built near renewable energy plants to reduce environmental impact. Another solution involves smaller models that deliver strong performance with fewer parameters. Techniques like model compression and knowledge distillation allow engineers to transfer intelligence from large systems into lighter versions that require less energy. Open source communities also contribute by sharing optimized training methods. When researchers publish improvements that reduce computation requirements, thousands of developers worldwide can benefit from lower training costs. Despite these innovations, the economics of AI remain challenging. The most advanced systems are still extremely expensive to create. This concentration of resources means only a small number of organizations control the most powerful models. This imbalance raises important questions about access and fairness. If AI development requires hundreds of millions of dollars, smaller companies and research institutions may struggle to compete. The future of AI could be shaped by those who can afford its hidden costs. At the same time, breakthroughs often begin with smaller experiments. Many influential ideas in machine learning originated from modest research projects using limited hardware. Creativity and new algorithms can sometimes outperform raw computational power. The story of AI training is therefore not only about money and machines. It is also about human curiosity and persistence. Scientists continue pushing the limits of computation to understand how intelligent systems can learn from data. Yet every new model reminds us that intelligence at scale demands resources. Electricity, hardware, labor, water, and infrastructure all combine into a massive industrial effort hidden behind simple user interfaces. When someone types a question into an AI assistant, the response appears in seconds. But behind that instant answer lies months of training, billions of calculations, and a network of machines operating across the world. The secret cost of training AI models is therefore more than a financial number. It represents the vast infrastructure required to build intelligent systems. As artificial intelligence continues evolving, understanding these hidden costs may shape how responsibly humanity develops the technology of the future.